So for our first section for Module 10, we're going to take a look at an introduction to the feedback control system. In a lot of the lecture this week, I'm going to spend some time going through some examples for different projects that I've done in my research and relate some of the stuff within this chapter to those projects. So within the chapter, a couple things that you should have be comfortable with by the end of the chapter is you should be able to model some common control system components. So we're going to go over the basic control system components, look at a couple of block diagrams of this. You should also be able to select an appropriate control algorithm of the PID type or one of its variations for an application for a given steady state and transient performance specifications. Third, we should be able to analyze the performance of a control algorithm for transfer functions, block diagrams, and computer methods in light of given performance specifications. And lastly, what we're going to take a look at the end of the chapter is some Simulink and MATLAB problems, examples, and coding for this section as well. So as we get into chapter 10, for module 10 for this week, what we're going to be looking at is feedback control systems. So as I'd mentioned, we're going to be spending a lot of time looking through some examples related to real life applications and some of the research that I've done. But I also want to cover what your assigned readings are for this week and how to relate this back to the sections within the text. So as we look through this here, we're going to be covering the basics of feedback control and show how to model control systems so that we can analyze their performance. That's the main thing that we want to do, is how do we analyze these and how do we write them down in a form that we can take a look at the individual components of these systems. So in the first section of chapter 10, we're going to just talk about the basic concept of feedback control, talk about open loop versus closed loop systems, the benefits to both of those. Then in section 10.2, we're taking a look at a little bit more of the terminology associated with the control system. And from there in 10.3, how the various components that we've looked at within these control systems are going to be modeled. So this right here, 10.1 through 10.3, will be our section 10.1 for module 10. And then we're going to move on for 10.4 through 10.7 for our second section of module 10. So this will be 10.2, or 10.4 in our textbook. We're going to take a look at the common control algorithm, also what's known as our PID algorithm there. Then in 10.5, we're going to look at the analysis procedure for general control system. And lastly, for this section here in 10.2, we're going to look at sections 10.6 and 10.7 in our text. We're going to be getting more into the performance of the PID control and variations of it. So last portion we're going to look at here for 10.3 is we're going to cover a couple additional examples at the beginning of this 10.3, module 10.3, then go over some Simulink for problems for the control system, and last we're going to take a look at a little bit of review of the chapter for the major topics that we went through for this whole section for module 10. So as we begin module 10.1, what we're going to look at here is closed loop systems, open loop, compare those together, control system terminology, and modeling of the control system. So again, this relates back to 10.1, 10.2, and 10.3 in your textbook. So I'm expecting you guys are reading through that as well to get your key equations and key concept for these three sections, for the closed and open control system, the terminology, and for modeling your control systems. So as we start off module 10.1, what we're first going to look at here is a closed loop control. So now if we're talking about just a control system in general, a basic one of these would be a timer that we use to turn off room lights. So it's either on or off. And you may have seen some of these. You can plug them right into your wall outlets, and they have mechanical ones and electrical ones. You set a time, okay, at 8 a.m. the lights are going to go off, they're going to go on, they're going to stay on until 5 p.m. at which time they shut off. So for a simple version of this, we just talk about a mechanical ones. There's a physical dial on it. You click, press the buttons down for the start time, for the on time, press the buttons down for the off time. It turns the lights on and off at those set times. So this is what we're called an open loop system. So this is due to the fact that there's not a sensor involved at all to alter the behavior. You just have this timer turning it on and off. Now, if we were to implement this and change it a little bit and have a light sensor, so as it got darker in the day, your lights turned on. And as it got brighter and the sunlight came in, the lights turned off. So now you're bringing in a sensor into the system, not just a timer. So by bringing and introducing that sensor into the system, this is now going to be a closed loop system. So this is primarily what we're going to be concentrating on for most of this section here in this module as our closed loop control. Now this term for closed loops kind of comes from our block diagrams for such a system, in which our sensor measurement is represented in a feedback loop. Now, even though we're going to be concentrating primarily on systems, closed loop systems involving sensors, there is a place for our open loop systems, and these can be used to supplement our closed loop systems. And as I get into some of the examples of the research and projects that I've worked on, I'll show how we have different options of how we can utilize the systems with some of the closed loop, with sensors and everything, and also in very simplistic times when we just really want it time triggered rather than sensor triggered, and we want to deal with just the open loop systems. So the first application that I'm going to talk about here involving these systems is a feedback controlled linear drive. Now we use this system for positioning our ground penetrating radar antennas in a test bed. So we have a sandpit test bed where we have various objects and targets that we bury down in here. So we have some landmines and circular plastic targets and cables that we have buried under the sand. And what we want to do is position our antennas in known spots based off of a given coordinate system. And at any point in time, as we're sending and receiving data through the antenna system, we need to know exactly where they are. So this is where a feedback controlled linear drive is going to be very, very crucial for us to know exactly where the antennas are at any point during the data acquisition. So a quick overview of this system here. We're using a network analyzer to send out our radar signals and receive them back. We're using a data acquisition system in order to timestamp and position stamp the data that we were receiving from the network analyzer. And we're triggering this data acquisition by the movement and position of the antennas on our linear rail. So as we were initially getting started with this project, we needed to figure out a way to accurately position and record that position for the antennas on our linear drive. So what we came up with is a takeoff on a block diagram here with some wiring and connection. So this is kind of our wiring diagram mixed with our block diagram that we utilized just to kind of map out how we were going to control the system, what sensors were going to be used, where is there going to be an open loop and a closed loop option for this entire linear drive system. So what we figured out was there's a lot of different sensors that we were going to need to utilize in order to run this system correctly. So we have over here on the left, we have the brains of our operation. So we're running this and controlling this all off of an Arduino. So we have our Arduino board, our microprocessor over here, and with that, there's power input, connection inputs, and then all of our sensor inputs. So this is going to be our main hub that we're plugging all of these sensors into. Now, when we're talking about sensors, we need to think about what the linear drive is, what the capabilities are, what the needs are. So we need to accurately move at a set speed the antenna cards and control exactly and know and record where the position is of the car at any given time within that motion. So we had a couple different options. We either have a constant speed, constant motion option, where the car just travels at an exact known speed, and based off of that speed, we can back out the position of the car. And as it's going, it's just constantly sending and receiving data. And the only way to link those two together would be a timestamp. So that is kind of a modified or hybrid open loop system there, because we really just have a timer. We say go, it goes, and it reaches the end, it stops. So the only real thing in there is setting the time of, okay, at this time we start the motion, at this time we stop the motion, and from there we just know where it is based on the fact that it's a constant speed, which has its ups and downs, positives and negatives associated with it. With a system like that, it's really dependent upon the fact that you have constant motion. So any disturbances, any errors that are introduced in the system that cause that motion not to be constant, all of a sudden your position based on that constant motion and constant speed kind of go out the window. So we decided that up top of that, we would really like a closed loop system with some sensors as well. So two of the sensors that we put into this are a bumper switch at the start and stop, so that we would know, okay, when it reaches the end, it stops. We don't have to program an amount of time. We just know when it reaches this point, it's going to bump the switch here and stop the motion. So we also have our input over here. We have a start button to start the constant motion of it there. We have a speed control as an input right there in order to control how fast it's going at that constant speed. And then from there we decide, okay, what if we really want to move it to a set position, at that position, send out our signal, wait for our receive signal, send it back to the data analyzer. Once it's saved and recorded, move to the next position, record that position, send out our signal, then save that signal, so on and so forth all the way through. So the first way to do this, what we did was a manual trigger button. So we're kind of moving away from an open loop system into slightly more of a closed loop system, where now it's going to be based upon us pushing this button. Every time we click our trigger button on this, it's going to move and advance the cart a set pre-programmed distance, stop it there, at which point we can send off the signal from our network analyzer into this, wait for a receive signal, we receive it in the network analyzer, goes into our data acquisition system. Okay, we see it, it's done. We can hit the button again, trigger it to move manually, which is a very, very slow process, and we still need to type out the file names for every single position. And if we're talking and moving in millimeter increments, that could be a very long day of doing that. So now we wanted to automate this process next. So we have a motor controller here that we've introduced here that we can send a step function to. And the way we've worked for this is now we've integrated this and tied it in with a couple of relays here from our network analyzer. So now it's a smart stepper system with a closed loop feedback in it. So as these antennas move forward to the new position, it will get a signal from our network analyzer saying, okay, send out our radar signal through the transmit antenna, receive it through the receive antenna, comes back up through our network analyzer program, realize, okay, yes, I've received it. Now I'm going to send out a TTL signal through our relay to go back to our Arduino board and say, okay, move to the next position. So that's how we've kind of gone from a very simple time-controlled open loop system to a complex multi-sensor closed loop system. And it's kind of tricky, as you can see here, with just the block diagram. So this is where we need to break things down within these diagrams to better understand each component and how to program this in. So as we go from our initial design diagram to actually building a control system involving all of these components, we can see it's great to have that simplified block diagram and our wiring diagram to reference back to as we're actually physically building a system like this, connecting it to all the different sensors we have, to our data analysis, data acquisition system, network analyzer, our motors. Everything here comes back to, again, our control system here. So what we've done here is we've literally put it in a black box. So on the outside, we just have our connections for all of our power input, sensors, and connections to other subsystems, the network analyzer and data acquisition. So we can reference back to our previous block diagram and wiring diagram there. We can see, okay, up here, now this is where I physically plug in my limit switches, my bump switches at the end to know when we're at our start point, our home position, and at our end point where we stop motion of the cart. So those are our two bump switches that detect that. We have our motor connected right here through this connection here to our motor controller. We have our power input for our relays. We have a power input for our motor controller. We have a toggle switch to turn on and off our motor controllers. We have our power coming in, but we need to turn it on and off. And this all needs to happen outside of our control box. Now, importantly here, when we're talking about our feedback control system, we have our trigger in and our trigger out. So this connects to our network analyzer to let us know, okay, yes, we've received a signal, we've processed it, go ahead and send out our transmit signal and move our cart forward, our antennas forward. We also have our control system here in order to reset our Arduino board, our power source for our Arduino control board, and then our manual control here if we wanted to switch this over rather than being a closed loop system just to an open loop time triggered system here. Now we can switch over here, so all of a sudden it's just going to move at a set speed and keep going until a set distance based off of just a time trigger. So a little bit of a breakdown of this system here to simplify it a little bit more to see what we have going on. So we have a closed loop system option for this here. So this is where we have our sensors involved with this that control the motion of our cart, the motion of our motors here. So what we have is we have our network analyzer that's going to send out a signal through our transmit antennas of our GPR, or ground penetrating radar system. So this transmitted signal is sent into the ground and reflects back off of our buried targets that we have in that sandbox. And these reflected signals are picked up by our receive antennas. So these receive antennas are connected to the network analyzer as well. So the reflected signal is sent back to the network analyzer. And this triggers the data acquisition system that's connected to our network analyzer to save the time and position along with the data. So we're going to take the data and we're going to stamp it with the time and position and save it with our data acquisition system. So now once this data is saved in our data acquisition system, a TTL signal is going to be sent out to the control box. So from our network analyzer to our control box. And this is going to tell the system to move the motor, step the motor forward and move the antennas to the next position that we want to collect data at. So then the cart reaches this next position, sends a signal back to the network analyzer saying, yes, I'm at this new position here. Please send out your next radar signal. So the network analyzer sends out the next signal through the transmit antenna. And we repeat this process of transmitting and receiving and moving and stepping the cart forward based off of this closed loop system and our sensors. And we repeat this process until the cart reaches that bump switch at the end. So that's how we know we're done. We've reached this here, and when it reaches the bump switch at the end, this signal is sent back to our Arduino control box, in our control box here, and tells the motor, okay, stop moving the antenna, reverse it, and move it back to our home position at a constant speed. So then the cart moves back until it hits our home or our limit switch there, and we can put in new test samples and go from there, run another test. So that was discussing our closed loop system option. Now what we're going to do is we're going to take a look at our open loop system option here. So for this, the system sensors are not going to be used to control or alter the behavior of our system. Instead, we're going to use a pre-programmed timer, and that's going to be used to control the motion of our antennas within our cart, on our cart. So within this system here, the speed is pre-programmed as a constant value. The cart is moved forward at this set speed, and the send and receive data through the antenna that we have set up is at set time intervals. So every half of a second it's going to send and receive a signal, send and receive a signal. And that's just pre-programmed in, no sensors involved. Then we're going to record the data and timestamp it in the buffer and save it for later analysis. So we're not even worried about stopping, waiting, saving to data acquisition. We're saving this all in the buffer as we go with nothing but a timestamp on it. And it's going to keep going until it reaches a predetermined distance or time. So that is our option for the open loop system as compared to our closed loop system where we had all of our sensors involved. So as we physically build the system out and go from that initial block diagram and concept up through a physical connection of all the hardware in our black box area, what we really need to spend a lot of the time on is actually programming this and coding it out. So we chose to do this on a simple Arduino. It's not a lot of computing power that we need for this project here. We really just are talking to our sensors to get that feedback control of our motors. So a simple Arduino and a motor controller, really all we need for our electronics for that. So it's low power consumption, low cost, and a little bit easier to program. So what we've done here is we've started our Arduino code, and one of the main things we really need to figure out here is we have this system on motors, and we need to translate the revolutions of the motors, the rotation and the speeds of the motors, to the actual speed and positioning of our antennas on our radar cart on that linear drive. So we took a look and we calibrated these out and found that it's 2,000 steps per revolution, and we want how many steps do we need in order to get the resolution that we need for our data acquisition to acquire the images of the underground buried targets. So that was a big portion of it, was calibrating and setting it up and translating from motor speed and position to physical cart position and speed. We also need to define all of our variables and what we're going to call them so we can reference back to this as we're writing out our code for the linear drive. We initialize some of these here as well within our code. So one thing that I can say that is important, and I know this is specific to this project here, but in general, even as you're doing some of your homework problems, exam problems, or just working through stuff on your own, and you're utilizing MATLAB, a key thing to do is for your own good, just so when you come back and look at your code, or if you hand the code off to somebody else, or if it is a homework assignment and me or the TA are grading it, is your comments of your code, what you were thinking. So the same as of why we have our homework set up the way it is for our format, where I really encourage you to write down, okay, this is the key equation I use, this is why I used it. That way, if you miss one little part of it, people can still understand, okay, this was the general idea, these are the steps that we're following in order to do that. So that's why within the code here, you can see we comment out on a lot of things that we're actually doing here. So this is the measure of the actual distance moved. This was our original reduction of our motor. So all this information is there. That way, if we're wondering why we entered a simple line of code here and say equals to 20, this is the distance in millimeters it steps forward for each trigger, we can reference back to how we came up with that, why we came up with that, or if we switched out a motor, switched out the gearing. Any of those number of things might change that there. So all this information for our gear reduction, our steps per millimeter, all that stuff is important to know within our comments of our code. It doesn't affect our code at all, but it is going to affect if we need to change something out in our system, change the speed, change the motor, whatever it may be. We can reference back to this. Or if this project gets handed off to somebody else, they're going to know where we were and how to modify it and move it forward to progress it. Within this, I've also coded, even though it's not part of our coding, I've also put in some comments here to talk about what we actually did in some of our electronics wiring. So in this case here, we needed to add a pull-up resistor in order to achieve what we need to do for our digital pin inputs on our Arduino board. And this becomes important when we are talking about these closed loop systems and all these different sensors we need to integrate. We want to make sure that they're all communicating together, they're all on the same timestamp, they're all working as they should. And a lot of that's in the coding and in how we physically build the system itself and put the electronics together. So I'll continue on with the coding a little bit. I won't get into fine detail of how we program this specifically for this one here, but I just want to cover some of our loops, our if-then statements. So this is where we can utilize all of these sensors that we've integrated into our closed loop system and program them in. So if that bump switch is triggered, what happens? So all the variable names that we programmed in, everything that we initialized for our variables there now become important. We need to set signals from low to high, because a lot of that signal that's coming out of these is just going to be a TTL or a square wave that comes out of it at a known amplitude and voltage. And from that there, we'll say, okay, when I see this go high, I'm going to do the next thing. So maybe reverse the direction of the motor, which way the motor spins. It might be stop motion. It might be send out a signal. So all that's important. So that's where our coding here, where we start talking about some of these if-then, and these loops are going to come into play for as we're coding in our electronics to take into account all these sensors in our closed loop system. And a little bit more here again. Even though we have the option for closed and open here, if we have the open, a lot of the programming is still pre-programmed in. We're not using the sensors anymore, but it's still all within the same coding here on our Arduino here. So we're going to set our times. Okay, this is our start time, this is our stop time for motion, this is our speed programmed in here, and all that's going to be included in our code as well. So now to give you a little bit better idea of what we have going on here, I'll have a little video of the system up and running, utilizing some of the sensors for our feedback control. So this is our linear drive. Our PNAX is the network analyzer, and our BenchView is our data acquisition system. There's our send and our receive signals on port 1 and port 2 of our network analyzer. So this is kind of a tutorial that I did, so if anybody were to come back and use it, this is how we do it. So first step is we boot up our network analyzer, and this is what's going to control, again, our signal in and our signal out. And this is also going to have our signal from our Arduino that triggers this to send out data, and our trigger out of this that tells the Arduino in the control box to move the carts forward. So even though our Arduino is our control box for the motion control of our linear drive, our network analyzer is also being used as a PC and a controller as well within this, and this is going to trigger back and forth between the control box and with our data analysis, our BenchView software. So computer boots up, it's going to load in our network analyzer software that we're going to utilize for this system here for our signals that we're using. So checking our frequency range, so that's one of the most important things here that we're sending out, is when we're sending the signals out, we want to make sure we're sending out the right frequencies that we're doing. We go through our whole setup process here, set all of our parameters, select our transformer. Are we in our time domain? Are we in our frequency domain? And we set our start and stop times within this here. So all of our signal for what we're sending through our antennas is programmed through this network analyzer here. So this lets us know, okay, we're sending out on port 1, we're receiving on port 2, this is the signal we're sending, this is the size of our signal, this is the amplitude, this is the frequency of our signal, and all of that is just the information for what's being sent in and out of our send and receive and signals that are then being moved on this linear drive. So there's a whole nother portion that we could get into here as far as transforms go, time domain, frequency domain, just for our radar signals that we're developing within this network analyzer. But for now, we'll just consider that a signal out and a signal in received and data acquisition communication with BenchView. We'll focus just on the motion control portion of our linear drive. So that right there is where we're setting up our triggers, our auxiliary triggers right here. That's what's going to communicate with our control box and let us know, okay, we've received the data, we've saved the data, now it's okay, move to the next position, send out the next signal, wait for it to get received, and then step forward again. So we're calling this a handshake between the two systems. So there's a lot, as we can see, as we're setting things up here that go into what the signal looked like that we're sending out and what they're expecting for the signal from the control box that goes back into our network analyzer. So we take a look at our whole setup. We have two different PCs, one running the BenchView communicating with our network analyzer, one running the network analyzer itself, and then the microcontroller that's running our control box for controlling the motor speed and motion there. So this over here now that we're looking at is our BenchView software, and what BenchView is this is our data acquisition software. So when the radar antennas on our linear drive receive the reflected data, it comes back and saves it on this program over here where it timestamps it and position stamps it with the information from our sensors within our system on the linear drive. So right here now we're setting our number of captures, so that'll be how many steps we move forward with our linear drive. So 250 steps over that about approximately 1 meter of the length of our sandbox there. So this is where it'll move forward, send out a signal, receive the signal, save the data, then move forward again 250 times. Now the nice thing about this data acquisition system here that you don't always have is we can physically watch our signal on it, and we're not just getting it as raw data, which has its pros and cons. Pros, you can see it. Cons, it takes a lot longer. So we're waiting, I think it was about 1.5 seconds for every single data point, every single position on our linear scale. So it took quite a bit of time to acquire 1 meter of data. So now we can go back over to our linear drive system. So we set up our data acquisition, we set up our signals that we're sending out through our network analyzer, and we go back over to our linear drive, and we can see right here, there is our control box right there. So that's everything we programmed in. Beneath it is our power supply for it. Now we can see our motors connected to everything as well. So there's our control box right in the center there. Power that up. Powers up our 50 volt supply, powers up our 5 volt relay, powers up our Arduino. So when we hit the reset button, this resets our Arduino, and I have it pre-programmed in for the code. So as soon as that Arduino starts, what it does is returns our cart to our home position. No matter where it is, it's going to move that cart back. And how it knows where it's at its home position is by these sensors. So it's going to keep moving in that reverse direction, which is where the home is located, until it hits that trigger, that sensor, which is that home switch, the bump switch, or limit switch there. So it'll slowly step this back at a set speed until we reach that bump switch right here. We can see right there, there's our sensor right there, our bump switch. Again, it's wired back into our control box over here. So our carts, our antennas all move back until we bump in to that limit switch there. And when we hit that there, it's going to stop the motion for us. You can see, click, stops right there. The limit switch is tripped. So now the linear drive's all set up and ready to go. We go back to the PC that's running our BenchView software over here, and we can run our data acquisition. So now we're at our start point. So now our testing has begun. The initial part was just to get it back into home position. Now everything is automated by our control system here. So as we're moving forward, you can hear it clicking. Every time it clicks, it's with the cart moving forward a step. We'll see that in a second here. So we come back over to our actual linear drive here. You can hear that clicking. Moving in 1 millimeter increments all the way across, 2 millimeter increments all the way across this while collecting the data and sending it to the BenchView software, our data acquisition software. So as you can see, as I mentioned earlier, this is a very slow process, but very accurate process. The reason we're moving so slow and in such small increments here is vibrations and movement of the antennas will affect our data. So we're trying to go slow, stop, send the data, require our data, click our trigger switch, go forward again, so on and so forth, until we get all the way to the end here. And you can see we have our limit switch at the end of this here, that once that is clicked as well, This will stop the motion and return it back to our home position. So we can zoom in right here. There's our end of limit switch here. So you can see up we have a little stopper right on the end of our linear drive that's going to bump right into that. And now you can really see in this close-up view the slow, precise, controlled motion. So this is why it's important when we're designing these block diagrams, setting up our system, doing our coding, doing our controlling, deciding how many sensors we have. We need to take all of this into account. So therefore, limit switch is tripped, it goes to the next position. So these vibrations, all these errors and things like that that occur during this are what's going to be disturbances. So as we move on, we're going to look at some of these block diagrams and talk about these disturbances and how we can adjust for them. Maybe more sensors, maybe multiple sensors, averaging algorithm, things like that all of a sudden become very, very important in building these systems out and integrating different sensors into them. So what we have here now is the results from this test. So now that we've seen what the physical system looks like, how it moves, how it uses sensors, how the whole control system works in a physical, practical application here, the whole point of this is to get this B-scan, the zoom B-scan image that we see here in the bottom right. And with this image here, what we're looking for is a reflection from our radar signal on these buried objects. So we can see here we have a cable that's buried, we have the round gray, and we have our landmine that's all buried there. And because we know the exact position at each one of these scans that we're taking, each signal that we send out, we can reconstruct this accurately and know the exact position of each of these within the sandbox. And that's what we're looking for, especially if we're talking about buried landmines or utilities or water and things like that. We want to know exactly where they are, either for a dig safe application or for just removing old inert landmines out of an old minefield, things like that. We really want to know exactly where they are. So this control system with all these integrated sensors becomes very, very important, so we get exact positioning for things that we can't see above ground. They're buried underground. We need to know exactly where they are, so all we can know for our position is where these antennas are. And based upon that information, we can say, okay, if the antenna is here and we're seeing this underground, therefore we know where each of these are relative to each other, relative to the antenna, and relative to a start point or an origin. So now we're going to take a look at some of the terminology we're using within this control system here, and then we'll get into a little bit more detail about the individual components as well. But if we're looking at this here and we're talking about our controller, so our feedback controller, what this is going to do is this is going to compare our command signal with the measurement of the outputs and decide what should be done next. So this is our comparison. Okay, if I have this and I have this and I see this here, what do I do next as a system? Do I move forward? Do I stop? Do I acquire data? So this is what our feedback controller is going to do, is compare the command signal with the measurements of the output and decide which we should do next. Now what we have here is the our control signal right here. So the control logic element produces the control signal, which is then going to be sent to our actuator or our final control element. So our actuator here. So it might be a physical actuator, it might be a motor, whatever it is. It's going to be the signal that goes to that, telling it what to do, how to do it. The object to be controlled is going to be the plant here. So in our system here, our object to be controlled is going to be the antenna, where it's positioned. And then the manipulated variable is generated by our final control element there. So whatever the manipulated variable here is going to come out of our control element right here. So this is just some of the terminology as we relate back. Again, we're going to spend a little bit more time and go to detail for individual components within a control system like this. So let's take a little sidebar here and let's relate some of this terminology to a little bit more simplistic system that we're all used to dealing with on a daily basis. We'll make a human analogy of this here. So if we're talking about a human body, our controller is going to be our brain, whereas our arms, our hands, or whatever is being held is going to be our plant. The arm, our muscles in our arm, if we're grabbing something with our hand here, this is going to be our actuator, the muscles. Our eyes are going to be one of our sensors. So eyes are going to take the role of a sensing element within this to know where we're putting our hand, where we're grabbing. And our transfer function here is going to be defined, as we saw in our previous thing, as our H of S. Now, the thing that we want to note here, that if the sensor gives error-free measurements instantaneously, then we have a value of H of S is equal to 1. And that's going to become important. Even though that's not a realistic practical application, it's something we may use for an assumption and simplification as we're doing some of our problems. So what this implies is that the sensor is going to respond quickly as compared to the rest of the system. So for example, the time constant is small as compared to the other time constants of the system. Now, something to consider that we talked about a little bit with our radar system and the antenna positioning is its disturbance input. So this is some type of input that we don't have any control over it. Something that could be happening externally. It could be from wind, it could be from a bump, it could just be vibrations that we didn't take into account. So all of this is going to be what we're referring to as our disturbance input. Now, we probably are going to have very little information available to us about what this disturbance is, what its magnitude, what its functional form is, what its frequency is, the time of occurrence. We're not going to know that necessarily. That's why it's going to be a disturbance input. It's something that we're going to need to possibly figure out. So from here, this again, some examples of this might be wind gusts for a radar antenna. Things that we really don't have control over but are realistic and going to occur. So how do we take those into account when we're doing out and designing our systems? And how we do that is a little bit tricky and a little bit of a judgment call and some give and take. So we want to make this as realistic as possible, take into account as much as we can. So what we say here is it's going to lie in the designer's ability to develop a model that describes the important behavior of the system. And that's the key word there, is we're talking about the important behavior of the system, because we don't want to be so nitpicky with this, including every little possible bump, disturbance, jolt, wind, gust, resistance, friction that may come in here that is minimal as compared to the rest of the output of the system. So we won't, because what's going to happen if we do every single thing like that, there's going to be so much detail and so much mathematical analysis, programming, everything, that it's going to be cumbersome, one, to develop, build it. It's going to be expensive. And on top of that, it's with programming like that, it could run very slow. So you're going to really, if you're going to want to include that much stuff in to the system itself, you're going to need to really work on your code to keep it clean so that your code runs smoothly, efficiently, and quickly. So another thing to consider as we're going in here is that things do not happen instantaneously. Now, as we're modeling out problems and talking about theoretical things, we assume, okay, yeah, I hit this button, it moves. Well, that's not reality. It is a time delay, and we're talking about things like radar signals and microwaves, and we're talking nanoseconds here. Well, something taking half a second or a quarter second to respond all of a sudden becomes very important as we're actually designing systems and programming them in. So all of these delays are going to be dependent upon us knowing exactly how to program it. So every actuator and every sensor is going to require this small amount of time in order to respond. And the question we need to ask ourselves is this time delay that it takes it to respond, is this important enough that we need to calculate this in, program it in, or is this close enough based on the rest of our time calculations that it's something that we can work with within our system? But it's something that we do need to consider as we're designing our systems out. So now we're going to look in a little bit more detail the individual components of this feedback control system right here. So we can see we start off, we have our RS. I've listed out everything down here. Our RS is going to be our command or our reference input going into our system there. This comes, now you can see here is our E of S here, or our air signal. Then we come into our controller. Over here we have a case of P, where a case of P is our proportional gain. Then we can see we have our F of S, or our control signal, coming out of our controller over here, going into our actuator. And within our actuator here, we have this function Ka over Tas plus 1, where our Ka is going to be our actuator gain right here, and our Ta is going to be a time constant right there. This comes over here into this junction here, where we can see we have our D sub S, or our disturbance that we talked about there, coming into our system from an outside source. Is probably unknown. So from this here, this is combined together, and this goes into our plant right here, where we have this function here, K over tau S plus 1, where K is going to be the gain here. And we can see this, we have our output signal over here, our CS, which is, this is going to be our control variable right there. This comes back down around here in our feedback loop right here into our sensor right here. So our CS signal, our controlled variable signal, comes into our sensor. Our sensor, we have this function here, which is our KS over our tau S, tau sub S, S plus 1 over here, where our K sub S is going to be our sensor gain. So this could be something like if it was a visual sensor or a touch sensor there, we could have an adjustable, so it's a certain amount of pressure, certain amount of light, certain amount of whatever. So that's our adjustability right there, is our K of S value for our sensor gain right there. This comes back up, feeds back in now again right at our beginning here where our input signal comes back in there. Thing to note that our control signal, our F of t here, is going to be proportional to our air signal, our E of t. And our time constants, the actuator and the sensor have both been modeled as first order systems for this problem right here, having the time constants we see our TA and our TS. So there's our TA time constant right there for our actuator, and our TS, our tau, or our time constants for our sensor down there. So we can see down at the bottom we have our CS over our RS here for our command transfer function. So we talked a little bit about the complexity of some of these disturbances that we're seeing coming into our systems here. So modeling these disturbances are not usually the easiest thing in the world. They're not going to be the most simplistic signals. They're not going to be something that you'd see the normal step or a ramp or a sine wave coming in as our disturbance. We oftentimes don't even know the exact function or form of the disturbance at all either. So could be just some random function such as a wind gust coming in and causing some torque disturbance input that's coming into our system. So analyzing these inputs is not something that we're going to cover within this course here, but it is a very, very interesting area. And it is something that's going to need to be dealt with. So a lot of times how we deal with these disturbances and how we model them in is to analyze them separately. Take a look at your system as a whole in a controlled environment where you don't have any outside sources. Call this your background control variable that you have there. And what you can do is if you have the system running with no outside sources, no wind, no nothing. You're in a vacuum, you're in a clean room, whatever it might be, to make it completely controlled in an unrealistic environment, and you have that information there. Then you run the same experiment in a realistic environment where you have noise, you have wind, you have dirt, you have dust, whatever it may be, and you can compare those two signals. And one way in which we compare these is a frequency response plot right there. So with these response plots right there, we can take a look at the signal with and without the interference, with and without disturbance, and try to extract it, do some transforms, Hilbert transfer, things like that, that we can try to back out what that disturbance is so we can remove it from our system and do that background subtraction. So we might call the disturbance our background in our real life application that we need to remove out of our system in order to analyze it properly. So the last thing we're going to take a look at in this section of module is our pulse width modulation. So one thing to note here, the voltage output of a zero order hold is constant over our sampling interval t here, but it's going to vary in amplitude over successive sampling intervals. Now the task of providing a variable amplitude voltage can be rather difficult, and this is due to the fact that the dynamics caused by motor inductance, things of that nature there. So instead of varying our amplitude, what we really want to do is keep that amplitude constant. So an alternative method for this is to use a constant voltage, but instead of than varying the amplitude there, because now we have that set steady at the constant voltage, what we want to do is vary the amount of time that that set voltage is going to be applied over some sampling interval here. So this basis is what we're calling our pulse width modulation. We can see a good example of this down in our graph right here. So you can see we have our low average voltage here, but we can see everything here keeping at a constant voltage there. What's varying here is our pulse width. So as we vary these pulse widths here, this is a different way, an alternative way to do this rather than varying our amplitude here. So now if we look down at our governing equation for this here, we have the TI is equal to our VC over V times T, where VC is going to be that average required voltage over our time interval, our T there, and our TI right here is going to be our pulse time that we can calculate from this relationship.